For joining this session. My name is Jay Palaniappan. I'm a solutions architect with Databricks. Today we're going to talk about how you can unlock your next-gen stateful streaming workloads using Apache Spark and transformWithState. So a little bit about myself. I like 25 years of experience in IT with more than a decade focused on designing and managing big data and AI applications on the cloud. At Databricks, I help customers build and run data engineering and machine learning workloads. Additionally, I'm a technical blogger and a speaker. I like to share insights and innovations that's happening in the data engineering field, especially with Apache Spark, to help others understand and excel in this field. So I'm looking forward to having this engaging session with you guys. So today I'm going to use a cool food delivery app-based demo that our DevRel team has built to showcase the capabilities of our stateful streaming framework, transformWithState. So I'm going to use like a concept called Ghost Kitchen. Many of you might have heard about it. Sometimes it's also called like dark kitchens as a business use case to showcase the capabilities of transformWithState. So for those who haven't heard of what ghost kitchens are, they are a shared kitchen where like your favorite restaurant might use to order food on their behalf. So these kitchens might not have any seating associated with it, but help deliver food for multiple brands. Now, ghost kitchens have a surprising amount of real-time data, right? Not only they have a lot of orders from different brands, they have a lot of customers and driver facilitations as well. So, so for today, I want you to pretend that like I'm not Jay from Databricks. I'm in fact an analyst for our ghost kitchen. And as an analyst, I have a bit of a problem. We have realized that like if there are significant delays in our food preparation or in our order pickup time by the drivers, the customers will never use this again, right? However, through our research, we found that if we offer them a partial refund before their food is delivered, they are much more likely to be a repeat customer for us. So, which means that we need to calculate in real time who's eligible for this refund. And for that, like we need to pull disparate data coming from different sources, like the order data from their apps, the food preparation data from the kitchen, and the delivery data from the drivers itself, right? And in order to like successfully combine all of this, we are going to use Apache Spark streaming and transformWithState API to identify who are eligible for those refunds. So for those who are not familiar with Apache Spark, let's review some basics, right? Apache Spark thrives in a massive open source ecosystem supporting Python, SQL, Scala, Java, and R. On Databricks, we have seen 30 million streaming jobs a week, a 60% increase since the last time we did this benchmark. All of them are powered by Apache Spark. It is engineered for scale, right? It is reliable, fault tolerant, and ready for the biggest data challenges. Some of our customers run hundreds of terabytes through Spark streaming jobs every day. Spark isn't just for streaming. It is a true all-rounder, right? You can do batch processing, you can do analytics, you can do machine learning, and even graph workloads. So just double clicking on it, like how does Spark work? So Spark is a distributed compute architecture. It is simple yet very powerful. It has a driver which coordinates with the executors to process computations in parallel. For example, as your Kafka or Pulsar topics grows with more partitions, Spark can scale out by adding executors and cores to its job. This flexible scaling lets Spark efficiently process massive streaming workloads, no matter how large your data grows. Some quick definitions to help you see where transformWithState fits in, right? So there are two types of structured streaming like pipelines you would see commonly. The first type is called the stateless, where each record is handled independently. No remembering is needed between microbatches. So these are used for simple filters and conversions use cases. And then the other type is the stateful data processing, where you need to remember the data and the records across microbatches, right? This is helpful for streaming and joins, and also for complex analytics, pattern recognition, and aggregations over time. So prior to transformWithState, you would do arbitrary stateful processing with a feature called a flat map group with state on Scala, or apply in pandas with state on Apache Spark. So some of you might be familiar with it. If you aren't, this is the first iteration of our arbitrary stateful processing framework. And the problem with that was it didn't have features to support multiple variables. So that means you're stuck with one single blob of data, and it didn't support schema evolution. So it was rigid. So if you want to evolve your schema, you may have to do start over all over again. And it has only one timer per key, which means that if you want to trigger multiple events based on different logics, you can't do that. And then last but not least, it had serialization penalties, and it kind of manifested at scale and become less efficient. So developers faced a maze of workarounds. Debuggability was different, and the performance were not par with some of the competing frameworks out there. So thankfully, we decided to build transformWithState. So with transformWithState, which was introduced in Spark 4.0, many of the challenges we talked about earlier were resolved, right? And it's already in production. Some of our, as I mentioned before, some of our largest customer run through multiple terabytes of data on it every day. It is safe to say that it is production-ready feature, and it works at scale. So how does a transformWithState work? So it uses similar sort of architecture because it runs on Spark. You have a driver which coordinates a job, and the data is processed in each of these executors. But each of these executors have their own embedded RocksDB data store where the state is stored. The API elegantly hides the complexity under the hood, and so it makes it easy for you to manage these states, which are managed by the RocksDB under the hood. What more, RocksDB stores its data as change logs, so which means that as and when the state evolves and the data is stored in RocksDB, it's transparently and durably stored in a cloud storage or a durable storage behind the screen. So this boosts durability, recoverability, and because the changelog is synced and not the entire RocksDB database, it's much more efficient and lightweight. So you get the power of all the distributed state management as before, without a lot of operational overheads. So you can just focus on your business logic, define your custom states as you want to solve, and then let Spark handle the rest. So let's talk about what it actually looks to implement transformWithState, right? First, you define a custom stateful class. This is where you set up the schema for your state. You can even add custom variables and TTLs to expire your state when it gets too old. You can write handlers to process incoming records. These handlers can read, update the state for each key, whether it's a single value or a list of values or a map. And then you have full control when you trigger this transformations, right? So it can be triggered when new records come in, or you can set custom timers and then process these logic based on your use case. In short, transform state gives you a set of building blocks to manage state exactly how your application needs, without any of the old limitations we discussed earlier. So now that you understand how transformWithState works, let's bring it to life with a demo. We'll show how easy to set up a custom state, process streaming data, and take full advantage of this new API in the real world scenario. Let's get cooking. So before we dive into the demo, I also kind of reiterate, what is the problem we are trying to solve for, right? So there are two use cases they're trying to solve for in this demo. The first use case is, the driver is late to pick up the food, and the food is hot, and the order was expensive, and we know for sure the delivery will take time. So that means we may have to give refund to our customers to make them happy. And the second use case is the item was received on time, but the orders, there are multiple items in the order, and the order was prepared a little bit late. Again, the rest of the conditions holds true, which is food is hot and expensive, and of course the delivery is going to get delayed, so we need to refund for that scenario as well. So within the transform state logic, we are gonna figure out these orders and process refunds. So what does this architecture look like at a high level? So we have event sources. That data comes from your ordering app, kitchen, and the driver, and then we pass that to transformWithState processor, which does its magic and figures out what orders or qualifies for refund, and then we pass it across to another system which will actually process the refund. For the sake of time, we're going to not talk about the refund processing framework. So let's go into how a transformWithState is defined at a high level, right? So we start with a simple group by, where we group by all the orders together as it comes along, and then we'll call this transformWithState and pandas API for Spark, for PySpark, and transformWithState if it's Scala. And within that, we will pass a transformer, the event data transformer, which is where our custom logic will be packaged. And then we define the output schema type, meaning the transformer, whatever data the transformers return, we need to put a shape to it, and the output schema gives that shape. And the output modes are the standard streaming output types, which is append or updates. And then the last but not least, the time mode, which helps us determine what time logic we need to use to qualify these records, whether it's event time when the event is produced, or the processing time when streaming actually started processing these records. Double clicking on the event data transformer, which is where our core logic is, there are two components in it. The first is the init function, where we'll define the state variables, where we want to keep hold of all the different states that we need to keep to determine if there is a refund needs to be made. And then the handle input rows, where we write our custom logic to see if a particular order qualifies for a refund. And then if not, it doesn't matter, then we will emit the records as and when deliveries are made. So again, reiterate, for each order ID, we need to compare for problem 1, when it left the kitchen, problem 2, when the first items completed cooking, and then the rest of the logic will be similar, like that is when it's picked up, whether it's still on road, what price it is, whether it's the food is hot or cold. Because for cold food, we may not offer refund because it doesn't have the time sensitivity as a hot food. All right, without further ado, let's jump into the demo. So the first part of the code, we created a set of synthetic data which contains orders, drivers, and prep information, and it has a specific schema. All kind of evolves around the order ID, which is the primary key for connecting all these data sets. And depending upon what type of event it is, then it has other qualifiers in them to figure out like whether it's like an order data, kitchen data, or it's a delivery data. And then we kind of write that data as a trickle-in data into a table called events. So in here we split the synthetic data into three types: orders, kitchen, and drivers. And then we write it in as an incremental data set into the events table. So this is the data prep. Now let's get into the meat of it, right? The actual logic which processes the data that is being written into. So as we discussed earlier, we are using RocksDB state store to store our data. And now let's get into the meat, event data transformer, right? And as we discussed earlier, it has the init function where we are defining all the required variables that we will find and store, right? First, we are defining here, which is like what's the first time the food came, the order came in, when it was finished, when it was picked up by the delivery person, and what is the price of the order, and whether the food is hot or not, right? Once the state is defined, inside the handle input rows, we start to collect the data as it comes along, right? So the rows value is what holds the data for every micro batch, for every key, which is the order ID. The data comes in, and then we iterate through those records and figure out what type of record it is, whether it's a order data or it's progress from the kitchen, or it's progress from the delivery. So all of that is figured out as part of this logic and stored in the state variables we declared up, right? So and I'm not going to go into details in each one of them. I'm going to now come into the area of focus, which is the refund logic, right? Assuming that the order came in, all the data is there for us to figure it out. So for what we do is we check, okay, when did the first order information came in, and when was the order finished, right? And if it's more than 20 minutes, we consider this as a delay order. And after, if it's finished, how long it takes for us to pick up, right? If it's picked up more than 5 minutes after, then we consider it as a delay. And then from the time it's picked up and the time it's delivered, if it's more than 30 minutes, we consider it as a driver delay, right? So these are key data sets that will help us define whether it requires a refund. So in this case, simple enough, if the pickup is delayed, if the driver is delayed, and the price is across above a certain threshold, in this case, we set it as $30. And if it is a hot food, then we know that yes, this is a high value order. We're going to miss the delivery deadline, so we have to refund, right? Once the decision is made, so we are emitting a record out here with all those key information, right? When it was finished, when it was delivered, what is the price, and then whether it needs to be refunded or not. So what about the orders that are delivered on time? We still want to keep track of it. Or at least in this logic we are keeping. So as soon as when the orders delivered and there are no delays, you still emit them with saying that no refund is needed, right? it's pretty much it. This is all the logic that is packaged. And then like we are defining the output schema over here. And then finally, we are just wiring all of it as we discussed. Like, we are grouping the order by order ID, we're calling the transformWithState over here and passing the event data transformer, like, logic over here and the output schema. And then I've been running this for some time, so just to make it easier to demo this. So as you can see, as and when the orders are delivered, it says like whether it qualifies for a refund or not. We see some like lots of false and few trues. There's also a nice, neat visualization in our notebooks that allows us to visualize the incoming data a little better. As you can see, for most part, we are delivering on time. The last hour seems like there's something weird going on where more orders are qualifying for refunds. There's some issue going on. Maybe we'll track that as part of another pipeline. So that kind of helps us walk through this, walk through how transformWithState works under the hood a lot better, I believe. So let's jump back into our deck, right? Again, so as of today, we see customers using transformWithState logic for multiple realistic projects and use cases. For example, ad sessionization use case where like you want to track impressions, click-through rates, and attribution, or like when a stream broadcasting data needs to be tracked for statistics, like how many users are watching this broadcast, or any other event related like aggregates you need to make. That's going to be tracked. And even for gaming use cases, for example, like if there is a gaming fraud is happening, or how many users are playing in a particular online game, all of those can be tracked and analyzed effectively using transformWithState. So we discussed like few key capabilities of it, but it also has other features that we didn't dive into. For example, the timer-driven event execution, or late and out of order data handling, or state access, which is a state store API. It allows to inspect how the data is being processed, and through the checkpoint data that we kind of manage for all stateful streaming data sets. So you can try all of this yourself from Spark 4.0. If you're a Databricks customer, you can try this on Databricks 16.1. I hope you were able to understand the transformWithState API a little bit better through this session. If you have any questions, feel free to type in. I'm happy to answer any questions. You can also reach me through LinkedIn or other sources. Happy to respond to those questions as well. Thank you for listening, and hope you have a wonderful day. Thank you.
All right. Thanks, Jay. It was great.
Awesome.
Yeah, thank you for giving the presentation. All right. Great. Now we can take questions from the audience. I see we have two questions, and you already addressed the answers, address them with the answers. But I think it would still be better to read them out loud, and then you can elaborate more, so the people who don't have a chance to join us, the webinar can watch later and see the answers. Will that work?
Yeah, sure.
Okay,
So the first
perfect.
question
Yeah.
is, how does the performance look like comparing to transformWithState in Spark structured streaming versus Flink? We have done some internal benchmarks, and the results are very positive. However, we haven't yet released that in public. There's a whole process how we kind of release these competitive benchmark, especially. So we we will release it in the future, but I'm not sure like when and what time it's going to be out. So, however, the core question is, does it perform better? Yes, in our test it is. Um, and the second question is, does transformWithState only work with streaming, or does it work with combining streaming and batch together? So it is a stream-only feature. It is built for arbitrary stateful streaming. However, like if your source data is not a stream, let's say if you have a delta table or like some format where you can play back the 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 evolution of the data, you can just read them as a stream. It's delta, it's like rather very simple. You can say dot read stream and you can read that data stream, and then you can pass it to transformWithState and perform the stateful operations. It's I don't know why someone would do that, because in that case it's you can run batch based sort of processing to figure out like what the value you want to get out of it. But long story short, transformWithState is only a stream only feature.
Got it. Got it. Awesome. Okay. All right. It looks like we have addressed all the questions. Unless there are more, I think this wraps up today's session. Thank you very much for your time, Jay, and I really appreciate you spending your insights and the presentation with us today.
Absolutely. All right. Thanks for having me.
Yeah, thanks. All right, bye.